Hey, this is my presentation for assignment 3. This assignment has two parts. The first part is about 2D convolutional kernels and how they work on images, and part B is about building and training a neural network on the CIFAR 10 dataset. So starting with part A, we just import the libraries like NumPy, PILs, SkyPy, SkyImage, and Matplotlib, and then we grab the image of the car from the URL, just like it requests us, and we load it into the NumPy's array so that we could work on it. And then if we look at the shape of this array, you could see it's a 3D array with the height, width, and 3 color channels for the RGB. You can also check the color channels are equal to each other and that they are basically a grayscale image stored in like a RGB format. And for the convolutional part, we created like a padded version of the image, and we started adding the borders around it, the borders of zeros around it, and then we define identity in the kernel, which is just a 3x3 grid, and with 1 in the center and 2's everywhere around it. And while we do that, we slide across the image and it gives us back the same image, which makes sense since we're only keeping the center pixel value of the image itself. Then there's a function called convolutional to kernel and 2D kernel, and this generalizes this. It takes any image in a 3x3 kernel and slides the kernel across the padded image. This allows us to multiply and sum the image and also clamp the values between 0 and 255, which is the RGB spectrum. And then they show us a horizontal line in the direction of the kernel, and it applies it to the car image, so you could see it picks up the horizontal edges pretty clearly. For question A, question 1, part A, I needed to create a kernel that detects 45-degree lines, so I made a kernel with 2's going along the diagonal bottom left to top right and -1's everywhere else. And then when we applied it, you could see it highlights the diagonal edges of the car. And then for question B, it was the same idea, but it was for 135-degree angle instead. And this time the 2's go from top to left and bottom to right. And the output just shows the diagonal edges in the other direction this time. And then we have question 2A. We had 3 edge detection kernels applied to it. The first one is 1's and -1's on the opposite sides, corners, and it picks up the diagonal edges. The second one is a Laplacian style kernel with -4 in the center and 1's on the side. It detects the edges in all directions. And the third one is similar, but with 8 in the center and -1's, and it gives us a sharper version of the edge detection of the image, as you can see from the different images. And you can see which one highlights the edges of the car slightly more and differently. Then we go to part B. Here we switch to building the actual neural net. So we import Keras, TensorFlow, load the dataset, and it has around 60,000 color images, and it has 10 classes, things like airplanes, cars, birds, cats, and so on. So we use one-hot encoding for the labels, and we convert those images to floats and normalize them between 0 and 1. So here we're just building out the model, and then we just custom callback for logging, and then we train the model and it goes through the model, and then we plot the graphs just for later. And then here we could go to question 3, where it asks about overfitting, and yeah, there definitely is overfitting. So if you look at the accuracy plot, the training accuracy keeps climbing towards 90% or higher, but the validation, it flattens out and even dips in certain parts. And you could see the two lines pulling roughly around like the 5th to 10th epoch, around that range. So this is where the model starts memorizing instead of learning to generalize the features. And then in question 4, it asks us write down how many layers the model has and identify it. So it has 5 layers. The convolutional 2D layer with the 32 filters. Then you have the max pooling 2D layer and the flattening layer that flattens it to a 1D array. And then the dense layer for the 128 neurons that goes through the ReLU activation function. And the final dense layer, which has 10 neurons and goes through the softmax function. And then for question 5, briefly explain what is the purpose of each of these layers. So the Convo 2D layer is a feature extractor. It slides those 32 filters across the images and looks for the edges and textures and stuff. And then max pooling shrinks the image by half by just keeping the max value in a 2x2 block, which reduces the computation it takes. Then the flattening takes the 2D feature and maps them and turns them into a single vector, so it's easier for like the computer to understand. Then the dense 128 layer learns which combinations of the features matter for classifying the image, and then the final dense 10 layer gives us the probabilities of each of the classes by using the softmax function. And then question 6 asks, add one or more convolutional layers to your model and run it again. So I added a second convolutional 2D layer with 64 filters and another max pooling 2D layer after. So now the network does 32 filters, pools, then 64 filters, and then pools again, then flattens, and then it uses the dense layers. And then it takes a while to compile, and after you could see the result. When you compare the results between the Aurelian model and the bigger model, I could tell you the difference is that the bigger model has better validation accuracy compared to the one we did before. As you see, it starts diverging around like 7/8 between the training and validation accuracy, and here it's slightly higher. That makes sense because the first convolutional layer picks up on like the simple stuff like edges, and the second one can combine those into more complex patterns, but it still overfits a lot. You can see the training accuracy is noticeably higher than validation, and the training takes a bit longer since there are more parameters. For question 8, we added a dropout layer to our model, run it, and compared the results to the previous one. So this is just adding the dropout layer. And then once it's run, you could see the validation accuracy versus the training accuracy. And basically, the dropout layer has a rate of 0.5 right after the 125 dense layer. Sorry, 128 dense layer. So during training, half the neurons in the layer randomly get turned off each step, and we trained it and we plotted it down here. Now, the difference between or the purpose of the dropout layer and how it works is basically it randomly shuts off 50% of the neurons on each of the steps. This forces like the network not to depend too much on any single neuron or weight, and it spreads out the learning all around. This way we help fight the overfitting because the model can't just memorize through a few key neurons. When you actually use the model for predictions, dropout is turned off and all the neurons are activated. So if you look at the accuracy plot, you can see the gap between the training and the validation accuracy is much smaller compared to the model without the dropout, and it helps the model generalize much more better. And that was the entire assignment. Part A kind of showed us how the convolutional kernels detect different types of lines and edges, and then part B showed us how to build a CNN model and add more convolutional layer improves it, and how overfitting happens, and how dropout layers help reduce it. Thanks for watching.